Well, thank you for coming, everybody. It's now 2 o'clock, so we'll go ahead and get started. This summer, we're focusing on mechatronics. You've probably seen a few emails come out regarding electronics and mechatronics. So we're defining that as how mechanical and electrical things play well together. Today, we're specifically discussing how engineers, usually mechanical, can use SOLIDWORKS Flow to reduce the development cycle for printed circuit boards and for predicting the heat distribution. In my past, I worked with some circuit boards, and I've had boards fail before, sometimes quite quickly because they were running at too high a temperature, and that was a setback because it was generally 3 weeks by the time we got a new board design, had it manufactured and shipped in. And that was the good failures because we caught those in the development cycle. Unfortunately, the ones that got away were running too close to the optimal temperature or above it, but still operated for a set amount of time, maybe a month, 2 months, 3 months. And when that happens, you get failures that have to, well, they cost a whole lot more because you end up replacing finished products for customers. So I would think most engineers and most companies want to do everything they can to predict those things ahead of time. And we'll today go through an exercise in how we can do that with SOLIDWORKS Flow, using SOLIDWORKS PCB to develop the circuit boards in order to anticipate those high temperatures and potential failures before we've built boards and seen failures of real parts. When I think of SOLIDWORKS Flow, I think of it as having three main focuses: the internal flow, the external flow, and electronics cooling. So you may be able to justify this software for one of those things. You may be able to justify it because it's used in 3 different areas of your company. But we'll just real quickly touch on those 3 things before we do a deep dive into the electronics. Cooling. So internal studies, or internal flow, these are the kind of studies that would be most relevant if you're designing valves, manifolds, piping systems, and such things. In a previous webinar in the spring, I discussed a poppet valve I designed 5 years ago without the use of any flow software. I was able to show how the fluid flowed through the valve, how much pressure was lost in the valve, where that pressure was lost, and you could see that I could have done a better job had I had a tool like this to begin with. If you're interested, that's available on our YouTube channel. I think it's called a Flow Overview. Nick Pusateri, one of our applications engineers, also did a more in-depth dive into a Venturi valve. That's available as well. Now, when I think of CFD, what always comes to mind, or computational fluid dynamics to me, is aerodynamics, the outside. Whether it's a Formula One race car, a fighter jet, a mirror on a pickup truck, SOLIDWORKS can be used to predict unnecessary drag, noise generation, and also to examine where lift occurs. In that same overview I mentioned a minute ago, I ran a CFD on a paper airplane just because I've always thought it would be fun. And way back, I had a friend who I think set the world record for longest airplane flight in 6th grade. It wasn't verified by the Guinness Book of World Records, but I always thought it was pretty cool. Study hall in 6th grade was a great time for learning outside of the usual channels, I guess. You can also find Ken LeVictor's aerodynamic study of a tractor trailer that he ran June 15 in our YouTube channel. So this is the reason you're all here today. We're going to take a look at heat generation in a printed circuit board. In this segment, we'll explore a few ways in which SOLIDWORKS Flow can help understand how heat is generated and then dissipated in a simple circuit board, which ultimately should lead to shorter design cycles and better products. What we're going to look at today is, for lack of a better term, a retrofittable LED light bulb for a can light. Well, it's not quite a light bulb, but it's not quite a light fixture either, so we'll just call it somewhere in between. For this project, we just picked up one of these things from our local home improvement store and took the circuit board out and pretended we were designing the circuit board for the first time. If you're doing lighting applications, this is probably what you do in and out. You might also be doing this with a power supply or motor controller. So Mark Talbot, our PCB engineer, or electrical engineer, he designed this board up. We used 22 LEDs and a constant, well, an LED driver, but a constant current source. And we modeled it up the first time. We said, let's use a green circuit board like most circuit boards you see. It's FR4. It's layers of fiberglass and copper. So I'm actually going to walk you through a few of the steps just in PowerPoint and basically spoil the story. And then at the end, we'll go back and look at some of the more in detailed methods of how you set it up, how I set it up, and some of the information that you can gather from that. So when I first ran this board, you can see that the average temperature of the constant current source, the thing on the right with a red hot spot, is 127 degrees C. Now the absolute maximum operating temperature on the data sheet was 125 degrees Celsius. So we know we have a problem, but this might be a problem that we wouldn't have caught initially. If it's that hot, it might run fine for a while, but eventually it degrades the electronics. The LEDs had a maximum operating temperature of 100 degrees Celsius. You can see those are way out of the realm of what's allowed for that product. So the next step was, we said, it's a simple circuit board. Can we make it one-sided and dump it on a chunk of aluminum, an aluminum core circuit board? Price is usually the same. For small runs, for larger runs, costs a little more. But you can see here we got a pretty decent gain in, I guess it's loss in temperature. The LEDs are now below the design temperature by 5%, which maybe isn't completely ideal, but we're in the realm of possibilities. And we're at 5 degrees Celsius below our average temperature for that constant current source. Again, we're in the realm of possibility, but not ideal. So my next step was, well, let's look at adding a heat sink. Can we get some of that heat out of the constant current source? And there's a couple different heat sinks available. We've got a pin heat sink, which is generally a far more expensive way of doing it. You could possibly do a metal injection molding or die casting if you were using zinc or aluminum. But generally you'll see something like this where you've got pins pushed into a plate. On the left you have something far easier to manufacture. It's essentially a chunk of aluminum that's been cut a few different ways. And then of course in the front here we just have a simplified, or the unsimplified version of that constant current source. Now a little bit about what an LED looks like. If you're not familiar with them, they generally look like a little piece of plastic with some yellow silicone or something. Looks like a phosphor coating in the top, but there's a copper heat sink underneath that. And I'm telling you this because when I set it up, I used copper as my default material for these LEDs. Even though it doesn't look like copper, there's a big heat sink in there which is helping to draw the heat away from the actual diode and hopefully transferred into the circuit board. So here's the original board. And this is the heat that we talked about before, 119 degrees Celsius on the aluminum board. And then with my pins, you see we get a drastic reduction of more than 10 degrees Celsius. I believe that's about 12 degrees Celsius. It was at 119. I actually see a slight increase in temperature on the LEDs, but probably within the margin of error for a CFD. And finally, we look at the lower cost one, and we see it doesn't provide near the cooling effect that we'd hoped or we'd gotten out of the round one. So at this point in time as an engineer, I would probably go back and talk to my PCB designer and say, what can we do? Because I think we're in an area of concern. 117, that's based on a, I think, 20 degree Celsius ambient temperature. What if it's 30 degrees? It's a hot day and there's not any AC. We're really going to be above, most likely be above that threshold. So let's talk about things we can do. So with that, I'm going to pop over into SOLIDWORKS and show you how I'd set this up. So this is the, I guess I'll call it a dump for lack of a better term. This is the PCB file or the step file that came out of SOLIDWORKS PCB. You can see the LEDs are all here. I've simplified the constant current source that concerns me, and I've removed a few components that really aren't necessary. This fuse here, for example. And just for the ease of simplicity, I didn't simulate any heat generation from these resistors, but you can do that either by calculating it manually, or if you have the electronics cooling module, which is an add-on to SOLIDWORKS Flow, by using the Joule heating module. So let's just walk through some of the steps. Generally, the wizard is for noobs, and you don't want to use it in most software applications that I've dealt with because it locks you out of everything and overly simplifies it. In SOLIDWORKS Flow, that's not the case. This is really the best way to do it. So I'm just going to name my project here. And I can choose my unit system. And what's really nice is I can modify it. So I'm going to start with the SI system because it's easier. But generally, when I'm looking at a data sheet, I expect to see my temperature in Celsius. So we'll just make a change right here. And it'll be an external flow, meaning we're not enclosing it, we're just letting air fly around it. There's no walls. And then we'll add in gravity because we have natural convection, and radiation to get rid of some of that heat. And we'll have heat conduction in solids because obviously that's the most important thing we're concerned with right now. And it looks like I have 20 degrees C as the default temperature. Just a little aside while we're here, we're doing this as a steady state problem, but some of our customers have applications where lights flash or lights will come on, or perhaps a motor will be on for 10% of the time and off for 10% of the time. Or you want to look at, maybe you have an initial torque curve on that motor that you can start it up where it draws a lot of power. And then as it gets up to speed, it reduces to a steady state. The same with the LEDs. Sometimes light bars on cars, for the first 2 minutes, they'll be really bright, and then they'll dim it back down to a steady state so they don't overheat the electronics. Something we can get into, but not today, maybe a future webinar. And then I just need to choose air as my default fluid. We won't worry about humidity today. And then I need a default solid. And as I said, these LEDs are primarily copper on the bottom, so we'll just use that so we don't have to apply it to quite so many things. And we'll assume that the air is not moving. So now, just like you're generally used to in SOLIDWORKS Simulation, if you've used it, you've got essentially a workflow from top to bottom on the left-hand side. You can add and remove things and edit them as need be. So because I'm not concerned with that much air, I'm just going to reshape my computational domain. And this is essentially the mesh boundary. So you're telling SOLIDWORKS, I'm only interested in what goes on in this little area. And of course, by making it smaller, it requires less time to solve. And I'll give it a little room for air. And then the solid materials apply very easily. We'll only do one here for the sake of demonstration and not to bore you all. But if I look at my IC packages here, I can go down to my SOIC standard package and apply it that way. And I guess I'll do one more. I'll apply the board. So a circuit board is a sandwich of copper and fiberglass. So the heat transfers real well, in this case in the XY plane, but not very well. So that copper doesn't, the heat will transfer out through the copper, but not through that layer of fiberglass real well. So we need to tell it which direction is different from the other two. In this case, it's Z. We'll just apply it to that board. Now what I did want to show you here is when I go to create a new study, say we've run this one and I want to keep it, but let's look at the aluminum version as well. I can just clone this study. We'll use the same configuration, although if I were choosing, oh, I guess we'll use a different one. the aluminum board, I put a thicker board on there. It will open that configuration and apply the same things that I did to it. So it's taking a little longer than I'm used to for it to chug here. But once that's done, you can see the board is now thicker. And I can just quickly change that material from my FR4 board to just a generic aluminum. And depending on how in depth you get into this, and as you use it more and more, you can specify 2 resistor components which more accurately simulate things. In my case, I just made an estimate as to how much heat is generated from these things. So I believe I went to heat sources, and I'll insert a volume source here. And then in the good old SOLIDWORKS way, I can just pick things from the flyout menu. So all these LEDs generate about 9 watts total, or that's the rating on the board. I'm going to take off a third of that right off the bat and say a third of it is going away in light. So I'm only dealing with 6 watts, and then we'll take one more off saying that it's being lost in our AC to DC conversion, and we'll put about a 1/4 watt into the LED driver. So we'll put this at 5 watts. Let's go 4.5, I think. Yeah, we'll go with 5. And then just like I did for that, I'll add we'll rename it first. I'll add a second heat source of a 1/4 watt. And these will usually be listed on the data sheet, what the maximum rating is for it. Oops. I had them already pre-selected when I did it. There we go. Then the next step would be to set goals. This is what's telling SOLIDWORKS what I'm concerned with. So I'll use a global goal here, and I'll say I'm only concerned with my temperature in the solid. And we'll do the LEDs. And we'll create a goal for each component, and then that LED driver as well. Oops, that's the heatsink. So this allows SOLIDWORKS to converge the answer and decide that it's finished earlier and more accurately, and also gives me access to plotting the results based on each of those chips and how quickly it came up, things like that, especially if we're doing a time-dependent study. And then finally, I want to refine some areas, like you would do in a structural simulation. These pins are going to be very important that we mesh them well. The board as a whole, not so much. So I can use a local mesh. I really like how this works. I can just, much like the computational domain, push some arrows around to get a tighter mesh in the area where I want it and not worry about it so much in the area that I don't. What this will do is allow me to say how many, it's going to make a little square mesh, how many times it can break that square or that cube into smaller pieces. And we'll say 3 for fluid, solid, and at the interface between the two. And now when I ran this, I did it as well for this array of LEDs, but you've seen it once, that's enough for now. So let's switch over to the results. I have the pin heat sink here and ready to go. And you can see I also added a contact resistance to simulate solder being between the LED and the board itself. So I'll start by showing you the mesh. This is a little different than simulation in that you have to create a, oops, sorry, wrong button. You have to create a cut or a surface plot to see the mesh. But you can see here, I've refined it quite a bit in this area, and at least somewhat more around the LEDs. This only really is relevant to solid meshes, but I can pick a solid or just solid components and then have the mesh painted on the outside of it. So you see my heatsink gets a lot of attention, my LEDs get some attention, and the board itself gets very little. Now I've created a cut plot that shows the temperature distribution of the fluid, so the air flowing around it. I can do multiples. This one's actually a little more interesting. You can see I've got some hot air happening here, and it's floating up as you would expect from gravity or from buoyancy of hot air. Where it gets really fun is if I want to look at how air flows through here. So this is what we call a flow trajectory. And I just put one using the face here to see where air came from and where it went. And as you'd expect, you need to adjust the temperature of that fluid, but you get kind of a cone, like a campfire, of hot air going up in the middle. And if I want to color code this a little differently, I can just edit the definition. We've got some nice controls here for just choosing the maximum based on the plot. Or it takes all of those pipes and picks a maximum and minimum from there. And I can probe to see, can I? All right, let's turn off my filters now. All right, it won't let me probe that, my mistake. Now we can also look at a smaller area. And this kind of threw me for a loop. When I think about it now, it makes sense, but I expected the heat to rise directly off of these cylinders, but it's really going more towards the overall heat of the LEDs because it's much greater heat. So that makes sense. It's just wasn't something that I thought of originally. Now I can also look at this slightly differently and say, this is everybody's favorite. Hold on. Show me the spheres. You can animate it. See what the air looks like going from it. And the one other thing I wanted to show today was just how you can put callouts on here like you would for a presentation, like I showed in PowerPoint there. And if I clone this from one to the next, all of these things will come through. So if I look at if I take this and clone it, change my configuration over to my rectangular instead of my pin heatsink, all of these cut plots, all of these surface parameter callouts will be there as well. So here you see I'm at 107 degrees, 96. We might need to spend a little more time tweaking it, but we are within the realm of realistic. The one other thing, sorry, I think I said this was the last thing, was the heat flux plot. This is going to be a little overwhelming. So we'll simplify it, but it gives a overview of where heat is generated on the board and where it's going to. So you see we have 2.5 watts getting transferred into the air. Some LEDs have more energy getting transferred to them, some less. Just to simplify this, I'll make a new one. We'll just see how heat transfers between a couple components here. The board and these three LEDs and that constant current source. All right, so it's a little more complicated than I thought. Shame on me for working without a net. But yeah, you can reduce this to show less components. Apparently I just didn't know how to do it on the fly there. So I won't waste your time going through that. If you're interested, reach out to your Fisher Unitech representative, or when they reach out to you, I'd be glad to give you a customized demonstration based on one of your boards or similar applications. So with that, well, I do have a little bit of housekeeping I have to do yet. With that, I'm supposed to tell you that we do have a specialized training deal going on this month, or I guess this month until the 9th of September. So if you're interested in getting trained, we have a 20% off discount. You can either use this code if you take it online or talk to your rep when they contact you about doing that. So with that, are there any